Okay, everyone, we will get started in 1 minute. Thanks all for joining and being so prompt. If you want, in the meantime, we are going to open up the chat feature. So if you want to post where you're from, we would love to hear that, and we'll get started as we go along. So welcome. My name is Kira Peltz. I am the founder of this coding school and the executive director of the QubitxQubit initiative. Yeah, this is a dream come true. So we're really excited to have you all here. Before we actually get started, we have a pre-course survey that is mandatory for everyone in the course to fill out. Gabby will be posting a link to it. This is just to gauge students' interest in quantum computing, kind of where you all are at. And this is a way for us at the coding school to really measure the effectiveness of this program. We'll be looking at, what your views on quantum computing are now, first where they are midway through the course, and then again at the end of the course. So please answer honestly. There's no need to look anything up. This is simply to really gauge your interest. So I'm going to give a few minutes for anyone that hasn't completed the form yet, and then we'll go ahead and get straight into business. Also, just as a note, please keep filling out the survey. The closed captioning that we do have, it is AI generated. It's about 80% accurate. So, we will try to, continue to ensure the captioning is as accurate as possible, but just know that there is obviously a bit of a lag from when I'm talking to when it comes up and exactly what it says. And then if we can create a poll, it would be amazing, Gabby. Gabby's our assistant program manager. I'll be introducing them a bit later, but a poll just making sure most people are done, we can get started with the rest of the presentation. Okay, we're going to keep on moving forward. Again, feel free, the next few slides, I'm just introducing the program in more detail. You can finish out this, or you can finish it out over the break that we'll have halfway through. But again, I want to welcome you all to our QubitxQubit Introduction to Quantum Computing with IBM Quantum. We are so excited to have you here. I want to talk a little bit about why we're so passionate about quantum education. We truly believe that a well-trained quantum workforce is the key to future social mobility, shared prosperity, and innovation for all. We don't expect all of you to love quantum or even go in and pursue a career or research in quantum computing, but we do believe that regardless of what you do, understanding the foundations of quantum is going to be really important, whether you want to go into policymaking, education, finance, the medical sciences, or really any other area. The future will be led by those of you who know quantum, and you're going to be at the forefront of it by participating in this class. Just to give you a little bit of a lowdown so far, there will be 5,000 students from 100 plus countries. For those of you already on Discord, I know someone's made a map of all the countries that students are from, which is really exciting. This is the first course that makes quantum computing largely accessible to high school students. Quantum computing is often not taught until the graduate level and sometimes at the undergraduate level, but we believe it's important that students are learning early on and that we can increase access that way. We're also dedicated to making sure that the future quantum workforce is diverse and inclusive. So over 50% of students in this course do come from an underrepresented or underserved background, which we are incredibly proud of. And then last but not least, students in high school are actually eligible to receive high school course credit. We are University of California A through G course accredited, as well as going through WASC accreditation right now. We have over 45 partner schools, as well as nonprofits who are participating in this program and offering this course for credit to their students. And just finally, you'll hear more about IBM Quantum throughout the course and later on in this presentation today, but we are so grateful to our collaborator and sponsor, IBM Quantum, who has helped make this possible and make this free for all students, so we can really increase access. Now, today's lecture is going to be broken down into two parts. The first part is going to be me talking about all the course logistics. It's not the fun part, but it is really important you pay attention. I'm going to be going through a lot of details that will make your life and our lives easier down the road. And then I'm going to turn it over to our co-instructors, Fran and Amir, who are going to start introducing what is quantum computing and why you should go quantum. Before I get into more of the course details, it's really important. All of you have agreed to the code of conduct. At the coding school, we are dedicated to making sure that this course and the environment that we create is inclusive and respectful of all. So please make sure that you are being respectful and really creating a collaborative environment where everyone can grow. I'll talk about this a bit later on, but I do want to mention it already. No profanities, no, messaging other individuals outside of, the conversations, just in the channels that you're already in. No unsolicited messages. It's really important everyone feels safe. I'll go into some more specific examples when we start talking about Discord, but please make sure you're agreeing to this. And anyone that does feel like someone has violated the code of conduct, there is a form to fill out, or if it's urgent, you can email us or call us directly. And as a community member, we're all in this together and we need everyone to be supporting this mission. So if you see someone who is violating our code of conduct, please message one of us, or again, fill out the form. Course norms. One of the things I love the most about quantum computing and just the field of quantum in general is the fact that we don't have all the answers. As everyone in this course will tell you, all of your instructors, your guest speakers, your TAs, there's still so much left to know, and no one understands quantum the first time around. We'd actually be quite concerned if you did. So really expect failure as a part of this process. You're not going to understand everything. I know Fran and Amir have a few points to mention about this. So Fran, do you want to jump in as well?
Yeah, so I guess you'll be hearing from me in a little bit, but I just really want to emphasize what Kira just said. You'll hear a bunch of different anecdotes about how failure is part of the process, but I guess for me, when I first was getting into the field, the first time I tried to take a quantum mechanics course, I really didn't have the mathematical background necessary, and actually at MIT, my sophomore year, I actually failed the first midterm in my quantum mechanics class, had to drop out. And it was only in my second time sort of taking the course that I really started to understand everything going on and was able to succeed in the class. So if you're struggling, just don't I guess, recognize that you're not the only one. And I don't know, Amir, if you want to add anything to that.
Yeah, I'll also jump in. So I also have a similar story to Fran in the sense that the first few times that I, started doing quantum computing, either taking classes or research, things weren't clicking exactly. There were still holes in my knowledge that, I didn't end up filling really until I had to get into teaching. And that's when you have to force yourself to learn everything. But, first time around, as long as, you guys enjoy the process, enjoy the course, get excited by quantum computing, the holes that will be left in your knowledge, you can go back and fill throughout time.
Definitely. Thank you both. So again, the key is, and something that we'll continue to remind you of, failure is a part of the process. You have to be comfortable with uncertainty and sitting with it, because that's really the way that innovation and amazing ideas come about. So be curious, be open-minded. That's far more important than acing everything and understanding it right away. This is not going to be like your other classes where there's always a right answer. This is maybe one of the first times in your life where the answer is not known yet, and you could be the reason that's actually going to come up with what the solution ultimately is. So now I'm going to turn over to who we are. Before I do, I want to mention something that's very important. Please do not go and try to contact anyone that's one of our course leads, our TAs, our administrative staff, our board of directors, our board of advisors. Don't do this on LinkedIn. Don't try to ask for their emails or find their phone numbers. I've already gotten a number of calls from individuals who have found my phone number. So please make sure that you're being respectful. Again, there are 5,000 of you. Our whole team is working incredibly hard to make sure that this is the best course possible. And we're not going to be able to answer individual questions, especially across a wide range of platforms. So stick to Discord, stick to the different platforms that we have to make sure that you can get the support that you need. And please don't violate this rule that we have in place. So our 3 course leads are Fran and Amir, who are co-instructors, and then I am the executive director. Amir is a National Science Foundation fellow, as well as a PhD candidate at MIT. He also leads the Intro to Quantum Computing class over the winter session at MIT. Fran is currently a Rhodes Scholar at Oxford, and in 2 years will return to Berkeley, where she will be doing her PhD at the intersection of machine learning and quantum computing. Our administrative team, they are the ones that are answering your emails, the ones that are verifying all of your information. They're making sure that everything is working smoothly and happening. Again, when you send 5 emails asking the same thing, there's another human. It's one of them on the other side of the screen. So please be patient. Please don't reach out to them directly. Use again the channels that we ask you to use. And again, this goes back to reading the handbook. We took a lot of time to put the handbook together. It's over 20 pages long. There are answers to all the questions you have in there. And if they're not, I promise you will add them after the first time you ask. Our curriculum development team. We have an incredible curriculum development team. They are responsible for all of the readings that you'll get. We have developed out a textbook specifically for this course that you'll be able to use and review and read through to complement the lectures, as well as they're responsible for the homeworks and the course notes. Our teaching assistants, these are the individuals that are going to be leading your labs each week. So they range from undergraduates to postdocs at prestigious universities where they're all studying quantum computing. They're incredibly excited to be able to meet with all of you and work with you this upcoming year. And then our advisory board, it really consists of leading quantum scientists and researchers in the field. We're so excited to have them. I could spend all day talking just about our advisory board, but just to point out a few of them. So Spiros actually is involved in physics consultation. So if you've seen Marvel's Ant-Man, Now You See Me, Spider-Man, Homecoming, Captain Marvel, he's actually consulted on those films. We have Umesh, who is one of the founders of the field of quantum computing, specifically quantum complexity theory. Scott Aronson, who is also on our board, actually was one of his students, and Fran is going to be another one of his students when she goes to Berkeley in 2 years. And then Ray as well was one of Stephen Hawking's PhD students. And he was the first famous for convincing Hawking that time does not reverse in a contracting universe, along with Don Page. So again, hopefully we will be able to have Q&As with most of our advisory board, and you'll be able to ask them questions about their journey or where they see quantum computing going in the future. And just as a final point on who we're thankful for and grateful for their support, IBM Quantum is, responsible for making this course all happen and ensuring that this course is free and accessible to all of you. So want to thank IBM Quantum so much. And I want to switch it over right now to Abe, who's the global lead for IBM Quantum Education, who will give a bit of an introduction on IBM Quantum. Abe?
Awesome. Thank you, Kira. Let me just very quickly get set up here. Hi, everyone. So it's really great to be with you today, and we're really excited to see so many people joining this quantum computing revolution. One of the things that I'm most excited by here is not only seeing the education and all the learning that's happening, but also to see the community that's getting built. The quantum computing community is fairly small, and seeing more people coming into the community and joining us and doing really awesome work, both learning and contributing to all the projects in the field, is really exciting. So I just thought I'd share a few words with you. Let me just quickly start sharing my screen, Kira. This might do something or break something, and if it does, I'm sorry.
I can stop sharing mine.
Let's see. All right. Should be all set up right now to start sharing screen. Are you able to see my slides?
No, I can't. Can anyone else? No, Abe, we can't see it yet.
Gotcha. I just realized I'm the one who messed up. I'm sorry. Hello again, everyone, and it's really awesome to be with you again. And as I said, the really exciting thing that we have here is the opportunity to be working together on this quantum education project with the coding school. And Kira, thank you for the opening that you've done, which is excellent. And what I wanted to start with is, again, highlighting how we're not just educating, we're not just talking about quantum computing, we're also building a community as we go. And this industry is perhaps very exciting for that reason, because all of you are joining a community where, as Kira said, you're going to be contributing not just to things that are known today, but also things that are unknown today. And we'll possibly have the next big quantum algorithm coming from all the learners here today. So I'm really excited about that. And so, as I mentioned, this is why we're very excited about building community as we go. So why do we care so much about building a community? And the reason is that most things that we do are motivated by and also enhanced by the ability to have a community. For example, the project that you'll be using, the software that you'll be using to run code on the quantum computers is open source. And that means as you're learning, if you find parts of it that you can maybe improve, if you find parts of it that you can enhance, you can contribute to making that happen. And the impact of that is that the broad community sees the changes that you're making and benefits from it. As you're learning quantum computing, just remember that there are multiple avenues for you to go to. We have multiple resources online. The open source software that I mentioned is called Qiskit. We have a Qiskit YouTube channel. We have a Qiskit textbook, which can help you see what the common quantum algorithms are and see how to implement them. And of course, we have multiple events going around the year that you can join just to get some hands-on experience and maybe even join more communities. And as we do this, the goal is to enhance not just the experience, but also the learning that you get in the process. And so if you're excited to get hands-on experience, mentorship from the team as well, don't forget that there are also internship opportunities that you can apply to. So the core reason, again, Kira said this in the opening, and we're fully supportive of this, is not just that we're trying to change the future of computing with quantum computing, but that we're also trying to shape the future workforce of computing as we know it. And that's why there's so much effort placed into building this community from the ground up in an inclusive and really exciting manner so that all of you can be fully empowered to contribute to the community. So as you're thinking forward of what careers you'd want to explore, this is just a picture that I've put here for you to see so that you can understand. It's not just that we're telling about quantum computing. These are the guidelines that we use even to hire within the IBM quantum team. So this shows you just the sheer amount of breadth about skills that you can have as you're thinking about where you can go. And so that means if you're interested in physics, if you're interested in math, if you're interested in computer science and so on, you can explore different parts of quantum computing and even join parts of the team in that regard. And so really the main takeaway from this is that given how interdisciplinary quantum computing is, given how it draws from all of these fields, the best thing you can do today is to really pursue something that excites you. If you really like physics, push very hard to do more physics. If you really like math, push very hard to do more math. And you'll find that there's some intersection where you can take advantage of what you know and bring that to quantum computing and make significant impact. As I mentioned before, we have an internship program. So what I would expect to see is from all of the people who are getting trained today to get some hands-on lab experience, we'd be happy to have some of you in our internship program. So don't forget to apply for our internships. And at the end of the day, the way to apply for them is by going to this link where you'd go to ibm.co/quantum internships. What we want to see is someone who's very passionate about quantum computing, someone who's excited to learn about quantum computing. And this is just a picture of some of our past interns at the IBM lab in New York. We're really excited to work with more interns and really develop skills as we go along. Okay, so I'll stop sharing screen here and maybe Kira, I'll give it back to you.
Awesome. Thanks so much, Abe. I'm going to go back to sharing my screen, and Abe will make another appearance to do some cool demos of things that you'll be able to do later in the course on IBM experience. Let me get back to presenting. Okay.
Thanks, Kira.
No problem. Okay, cool. Okay, so a bit more about the course before now we'll get into like what the course actually entails and go through that. So course objectives, I think we've largely covered them, but just to reiterate again, we want all of you to succeed in the future. We want all of you to pursue the careers and the paths that you want to, and we do believe that learning quantum computing will help you get there. So we want to introduce you all to the field of quantum computing, have you all develop out the skills, real tangible skills, so you can continue to pursue this in the future, whether that be through university or internships like Abe had mentioned, or through your actual careers and jobs going forward. We also really want you to form this community. We want, you all are the future global quantum leaders. You are some of the first high school students that are really going to get in-depth quantum knowledge from this course and beyond. So definitely meet each other, definitely talk with each other. And hopefully down the road, we'll also be able to do programming where we can bring all of you together, in the future. So course components, there are 3 main weekly components to this course. There's the lecture, which you all are here and attending. This will be every week, every Sunday from 2 to 4 p.m. Eastern Standard Time. The breakdown will be about 1 hour of theory and a 1 hour tutorial or a walkthrough of some application that you are learning in the lecture. The recordings will be available if you are unable to attend the lecture. It's no problem. Obviously, we love you attending, and we will increase participation of students asking questions and things like that as the course goes on. But we understand time zones and differences may limit your participation in the actual lecture. All of those will be led by Amir and Fran, or sometimes we may have a guest lecturer or speaker come in, or a panel discussion. Every week, there will also be a lab. Now, you will receive more information this upcoming week about labs. So don't worry, there is no lab this week. We will send out more information. There will be labs Tuesday through Saturday at various times to accommodate various time zones. And again, if you can't make the lab, there are other ways that we can make sure that you are watching the lab recordings, and so you can get your participation points. Homework, that's the last piece of this. There will be no homework for this week, so we'll talk about this more again next week, but there will be weekly problem sets once the course actually begins next week. It will be graded on a pass-fail basis. I'll talk about grades a bit more later. The goal is not to stress you out. This course is not meant to be stressful. It's meant to be fun and interesting and engaging. We simply want to make sure that you actually are trying and putting in the effort to make sure that you do well in the course. So I'll talk more about grades next week, but that just gives you a little bit of an overview. You also have a full week after the course, after the weekly lecture, to complete the homework. So course syllabus, first semester is largely going to focus on the foundational skills that you need to be able to do quantum computing. So there's a lot of math, programming, some physics concepts that you'll be required to learn. So for some of you, these math concepts or programming concepts may be a review, and this first semester might be a little bit easier for you. With that said, we're going to do everything in our power to make sure that we're actually not just teaching you the math, but that we're applying it to quantum computing and quantum mechanics. So you are learning new things while this first semester goes along. Second semester is really where we start delving into the field of quantum, going through quantum mechanics, quantum information, and quantum algorithms. Now, some of the things that you will learn in this course, you will learn about quantum mechanics. You will learn how to program quantum circuits, and you will actually get to program on a real quantum computer. And so instead of me just talking more about this, I'm going to flip it back to Abe again, who is going to actually show you some of the really cool things and simulations that you'll be able to run. Abe, are you good to share your screen?
Absolutely. This is the fun part, right?
It is the fun part.
Let me start sharing the screen very quickly. So, share screen, and hopefully you're all able to see my screen right now. So you should be seeing a page that says real quantum computers right at your fingertips. Is that right?
Yes.
Awesome. Okay. So the first thing that I would really like to point out is that all of you are in a quite exciting time in quantum computing, where you don't need access to a lab anymore in order to run things on real quantum computers. Now that we have quantum computers online, this is one of the benefits that you have as you're learning. You can learn everything as you're building up by trying it on a real quantum computer. And I can't stress how cool this is. I think a number of people here who are going to be part of your teaching staff are also people who have to go to labs to access quantum computers. And it's just really cool that the shape of the field has changed from needing that access to being able to run things on a quantum computer. So by going to this website, quantum-computing.ibm.com, you should see something that gets you to a page that looks like this. If you've created an account here before, that's fine. You can sign in. If not, you can create an account. And as soon as you do, this is the page that I've opened it in a new browser window, but I actually have an account. You should see something that looks like this. Let me just very quickly start clicking here. And there we go. Yeah, so you should see a page that welcomes you and looks a little bit like this. Your page might be a little different with the number of quantum computers that you have access to and so on, but really the structure of the page looks like this. you're welcome to the page, and immediately on the right side, again, I can't believe I am saying this right now, but there are quantum computers that you can run code on, and there are multiple of them. It's not just one or two. So you can choose any of these quantum computers to run code on. And really what you're going to do is choose different ways of writing code on these quantum computers. So as you're learning, the best way to start learning and thinking about how to run things on quantum computers is by building quantum circuits. So quantum circuits are the bare bones logic that you're running on the quantum computer. And when we say circuits, really, it looks like the following. So if you go on the left side of this page, you'll see something that says circuit composer in the middle. The circuit composer will take you to something that looks like an interface that has Lego bricks. So different colored blocks here and different lines here. And what you can do here is each of these blocks are the gates that you apply onto your qubits, which are the quantum bits with which you'll be operating on the quantum computer. And what you're going to do is drag and drop some of these gates so that you can then act on the qubits in some specific manner. You can also remove specific gates once you've added them by clicking on the gates. And really, at the end of the day, what you're trying to do with a quantum computer is apply some gates and then do some measurements to see what came out of running on the quantum computer. So the measurement button is right here. Now, I want to show you a couple of neat things here. So if we stay on this page, you'll notice that this action of building out a quantum circuit is where you're drawing the quantum circuit and constructing what you're going to be run on the quantum computer. And before you run on a real quantum computer, this interface called IBM Quantum Experience tries to show you what the expected results are. And you can see it's already doing some computation here, telling you if you measure this circuit, which looks like it has 2 qubits, these 2 lines that you see here, and the gates that are applied on these 2 qubits, the operations are applied in the sequence that you see here from left to right. If you run it in this way, what you expect to see is the following outputs, 0, 0, and 1, 1. And so what you'll find is the tool itself is trying to tell you how things work and trying to show you how these quantum circuits would work if you tried to run them on a real quantum computer. You'll learn the visualization tools as you go throughout your course, but really what's important is that you can look at the results in one way or in another, both of which are shown to you here. This Q-sphere is another way of visualizing the results that you might expect with 0, 0, and 1, 1, which are the same things that are being shown to you, just in a different method of visualization. And all of these things will make sense as you cover the mathematics preliminaries. But one of the things that I want to show you is something that you can do with quantum computers that you can't. So once you've built out your quantum circuit, the next thing you can do is really run it on a quantum computer by picking a quantum computer here. You can choose your run settings. You can choose a quantum computer from this drop-down box, and then just click the run on that quantum computer button. And when you do this, that job gets sent to the quantum computer through the internet, and the quantum computer runs that circuit that you built and then gives you back the results. And when the results come back, they show up on the page here. So just to give you an idea of how this particular quantum circuit works, I've built a quantum circuit here already. So all I need to do is just click the run button on the quantum computer. And the moment that you do, you'll see that the run button immediately starts sending the job to the quantum computer. And the job gets queued on the quantum computer. And it looks like it'll take a few moments to get the results back from the quantum computer. So I've already constructed this circuit. You see the job has already gone to the quantum computer. It's now running on the quantum computer, and it'll take a few seconds. And then once the job is done, you'll get the results back from the quantum computer when it tells you that the result is completed. So these are past jobs that I've sent. So this is running. We'll give it a few seconds to run. And once it finishes up, if you click on this button, you'll see that this is where the results of your run show up. Remember, I said the results that you expect to see are already displayed for you on this screen. So in this particular one, you have 0, 0, and 1, 1. The results that we get on the real quantum computers, I can just, while we're waiting for this, oh, it's already done. While we're waiting for this result to be done, I can open it up and show you what we got from executing that quantum circuit. And you see, indeed, this was the circuit that was executed on the quantum computer. And the results came out, we did that circuit 2,000 times. And the results that came out are 0, 0, and 1, 1, roughly 50% of the time, and a very small number of times where you see the results 0, 1, and 1, 0. And again, as you go through the course, you'll understand why these show up on the real quantum computer, but not in the simulations that you saw in the earlier page. So that's step one. Step one is really building out your quantum computers, your quantum circuits in this way and running them on quantum computers, really by dragging and dropping and doing your measurements and trying to interpret the results that come out of what happens if you run these on the quantum computers. Now, the other thing that I want to show you as you learn more about quantum algorithms and how these quantum computers are really operating, what you might want to do is, because it gets very tedious to put down so many of these quantum gates one by one, you might instead want to write code to build out these circuits. And the interface for you to write code is also built into this website. We have something called a quantum lab, which again, on the left side, just below the circuit composer, is what you see here to be a quantum lab. It looks like an interface that is basically Jupyter Notebook. So effectively, you're writing Python code to build your quantum circuit. So this is the same quantum circuit that we built. We had an H gate on one of the qubits, a CX gate between the two qubits, and we did a measurement. And again, if you write this Python code and you run it, you'll find that you get similar results from running on the quantum computer. It's just now, this is a different way of building out these quantum circuits. And as you build out more and more complicated quantum algorithms, and near the end of your course, you'll have an understanding of how many qubits you need to solve certain types of problems, it really becomes crucial to use the code interface. So we're really excited for you to learn these and to master both interfaces and use whichever one is necessary for your work. So with that, I'll conclude by reminding you again, the website where you access all of these things, the quantum computers, the interface to build out quantum circuits by hand by dragging and dropping, and this Python interface is quantum-computing.ibm.com. If you don't have an account there, I would encourage you to create an account there so that you can access the quantum computers and run things on them as you go along. All right, I hope that's helpful. Kira, I'll pass it on to you.
Awesome. Thanks so much, Abe. I'm very excited to be using IBM Quantum Experience as well. Cool. I am going to go back to sharing my screen. Awesome. Okay, so let's talk a bit about technologies and communication more generally speaking. Piazza and Canvas, we're going to be releasing in the upcoming weeks, so you do not need to worry about either of these right now. The only platform that is launched for all of you is Discord. Again, I want to make just a general point. There are 5,000 of you in this course. We've used these platforms to make sure that you are receiving the support that you need, and we're leveraging technology to make sure that this is possible. So please use them in the way that they are outlined in the student handbook. We will be, moderating and make sure that you are using them appropriately. But your first, you should try to use Piazza, Canvas, or Discord throughout the course as your first way of communicating and getting more information. Discord, I'll focus on specifically right now, since that's the one platform that we're using. Discord is the way that you're going to communicate with one another. It's how you're going to form your community and how we're actually going to communicate with all of you as well, how we're going to release course announcements, reminders, the lecture videos after, the lecture today. So please make sure you all are on Discord. I know some of you still don't have your IDs or things like that. Don't worry, we're going to get that all to you. We'll also be adding in some more live verifying sessions, so that way you can be verified in real time. So just check back on there. Please make sure, again, you're using the correct channels and you're not spamming the account. Just a few other reminders and things I want to mention about Discord. I know many of you are new to Discord, so it's just going to take a bit of time to get used to. But one, Do not spam the group. Do not use profanities. Do not, use hate speech or engage in really divisive political rhetoric or other forms of divisive or harmful rhetoric. First and foremost, this group is for all of us to make sure we can communicate about the quantum course. So please don't derail it and derail that mission. Second, do not message individuals unprompted. This is particularly important for those that you may be messaging of the opposite gender. Power imbalances continue to exist, and a seemingly innocent message to one person may make another individual uncomfortable. So do not message people unprompted. Do not engage in individual communicating unless it's open and welcomed and both parties have agreed and want to continue forth. Also, at any point, an individual, even if they are engaging in a conversation with you, can decide that they no longer want to, and it is important for you to be respectful of that. 3, we will be doing the live verifications going forward and continue to verify all of you. Again, follow the directions. They're very clearly laid out. Many of you are not following it, and it's taking us a lot longer to go through the verifications. As we mentioned, it can take up to 24 hours. It can also take longer because of many of the additional issues that we're trying to go through with people not putting in their right IDs or things like that. And again, finally, use these channels the way that they're supposed to be used. We lay out how the channels are, what you're supposed to talk about in the student handbook. So please refer to that if you have any questions, but only be posting in the respective channel that you should be, and make sure that you're keeping them clean. We will delete all communication that is not adhering directly to the conversation at play. Again, code of conduct in place. If you see a violation or feel uncomfortable in any way, please report that to us. It is very important. And please use the Discord for general communication and to get questions answered. IDs, or again, if you are a student from a partner school and you use your school ID, there is a good chance that we're not able to send emails to you. So please send us a personal email so we can update your contact information as well. Again, lots of messages and communication coming in. Please be thoughtful before you send something out, and make sure that you've read over the handbook and looked through Discord first before reaching out to us. Homework, attendance, and grading. Again, as I mentioned, this course is meant to be fun. It's meant to be interesting. It's meant to be engaging. It's not meant to be stressful. Yes, quantum computing is difficult and it is a complex subject, but with that said, grades are not supposed to stress you out. They're really just a way to hold you accountable, to make sure that you are staying up to date with your assignments, and for us to also get a gauge, are we presenting this in the way that's making it most accessible to the most number of students? So if at some point, like, we will be monitoring how we're grading, and we are open if we need to lower certain thresholds for homeworks or other things like that. But again, just know that this is not meant to be a stressful experience. If you are doing this course through a partner school and receiving a grade for it, we will have more information about that separately. But just, yeah, any questions on this, we will talk about this more as the course goes on. Again, as you can see, the components of the final grade, the lab attendance, if you're unable to attend a lab, that's okay. We'll make sure that we have a way to mark that you have watched the lab recording. So don't worry about your grade being, subjected to anything there. But we do ask in terms of attendance that you do attend the live sessions as much as possible. It is important for learning and engagement and staying on top of the subject matter at hand. And now my last slide before we get to the fun things. Again, communication, I cannot stress this enough. Only email us if it's a specific question about your ID and not having your ID, or anything that has to be really specific and you can't find out over Discord or another avenue or through the student handbook. All of you have agreed that you are committed to taking this course for the entire year. We are going to have a massive wait list for this course, and many students will not, we're not able to get in as opposed to all of you. So this is a commitment that you all have signed up for, and it will be well worth it. I promise you that, but definitely you have to make sure you're willing to commit. There are going to be several breaks throughout the course. They're noted here. They're also in the student handbook. And then if you think your high school may be interested in offering this as a 4-credit course or an after-school enrichment course, please reach out to us. And additionally, if you're looking to receive course credit for this course, email us and we can provide more information that you can contact your school with. And with that said, we're going to take a 10-minute break right now. So at 2:55 p.m. Eastern Standard Time, 10 minutes, we'll be back and I'll flip it over to Amir and Fran, who will get us started on what is quantum computing. Thanks, everyone. Answer them. Okay, so which email should you use to contact us? So again, if you do need to contact us, and let me make sure this is sent to everyone, use our student email, student@QubitxQubit.org. So that's going to be the point of contact. Don't use another email. This email address is for all admitted students. And also don't share this with your friends if they're applying. If my school's interested in offering this course for credit, would it still be pass fail, or is there a possibility for another form of grading? No, we can do letter grades. That's completely fine. We are doing that for a number of our partner schools. So that's okay from our end. And like I said, this course is accredited for students to receive credit, but it has to be, your high school ultimately has to approve it. Is it necessary to have any programming knowledge before this course? No. While it's advantageous, we will teach you everything that you need to know. So that's fine there. How does course credit work for the UK? It really depends on your school. So you can feel free to contact your school and see what would be required. You can also email us at the beginning of this week. We'll have a kind of handbook for students looking to request high school course credit, and we can send that over to you, but it will be up to your individual school. And international schools are, all have slightly different protocols. Some will accept the US course accreditation and others will not. Abe, could you answer about the IBM quantum internships? Is it just for undergraduates? Who's that for?
Yeah, so I'll post a link in the chat shortly. We have internships for undergraduates, graduate students, and postdocs. So really the whole range of students. And I'll put a link where you can find all the job listings right now in the chat.
Awesome. Some other questions that we're getting. I'll stay on after the whole lecture finishes and take more questions that will be open, because we just have a few minutes now. For the first semester, will it be really easy for a second year math university student? Again, as we mentioned, many of this may be review for the first semester. We will be linking concepts to the applications of quantum computing. So there will be, it will be more than just math classes that you've already taken. But with that said, a lot of the math will be a review. So you will have a much lighter load first semester. Will grades be affected if we watch recorded sessions and can't attend the live sessions? No, that is fine. Again, we will have ways to ensure that you are watching the recordings and and just watching them and making sure that you're completing, the recordings and the homework in a timely manner. So that will not affect you. Okay, if some students have requested course accreditation and their schools don't allow any courses outside of their high schools, will there be a separate transcript up to send off to my university of choice? So we will be providing a certificate of completion upon completing the course. We will also be able to provide a unofficial transcript that discusses kind of what you did in here and that you passed the course. So yes, we can do that. You also are welcome to put this on your extracurriculars. This is a big time commitment. This is an amazing opportunity. This is something that will really distinguish you, as you are one of the first high school students to really get in-depth knowledge. So definitely feel free to do that. The Discord invite link. Rachel or Gabby, if you can post in here, that would be awesome. The homework deadline it really depends on your time zone. Whether it's Saturday or whether it's Sunday, it is 11:59 p.m. on Saturday night, East Coast time. Again, if there's any confusion about that, I'll make sure to clarify in the Discord channel. What happens if you don't pass? Again, as long as you are trying and actively making an effort, we are making sure that you will pass the course. If there are problems, if there are a large number of students that are having difficulties, we'll find ways to make sure that you receive the support that you need. So please don't worry about that. One additional thing, we will likely be implementing office hours as well that will actually be peer-to-peer run. So we'll be asking for students who are interested in that, especially those of you who may be older or have kind of advanced math skills and want to help out this semester. You can lead some office hours and students will be able to get more help and assistance. Also, the lab sessions, that's going to be largely, it's not review, but it's going to be going over similar problems that are going to be on the homework. So you will be getting support there. And Akshay is actually on the call, who's our head TA. Do you just want to say hi and introduce just the kind of the lab pedagogy and philosophy behind them? And then after that, we'll kick it off with the second part of our presentation.
Yeah, thanks, Rachel. Thanks, Kira. So hi, everyone. My name is Akshay. I'm originally from India, and I'm now living in Boston, Massachusetts. So I'm going to be the head TA. And we have 7 other wonderful TAs. You'll be meeting them in your lab sessions starting not this week, but the next week. And the idea behind the lab sessions is really to give you more of an opportunity to work through some problems that are similar to the homework problems so that you can get really comfortable with the math that goes into a lot of the quantum computing that we'll be discussing in the second semester. So that'll be a time where you can, we can slow down a little bit, discuss specific questions. We'll also have time to discuss questions that students have about the previous week's homework, about anything else that's going on in the course. And as I said, we'll have plenty of TAs to answer those questions. The lab sessions will be 1 hour long, and it'll really be a time for us to do some more direct interaction with each other.
Amazing. Thanks so much, Akshay. Just two more things and then I'll flip it over. So we will, we'll send out information to everyone about receiving high school course credit and what the protocols will be. That'll be much easier actually than all of you emailing us about it. So disregard emailing us unless if your school does want to partner with us. We had a number of students from our summer course who, you know, reached out to their school and they've started a club either after school or, you know, actually integrated into the school day for course credit. Definitely let us know. And then again, as I mentioned, we will be sending out more information to everyone about that. The second thing, so this is the orientation. Our applications are still open, and the official course launch date will be next Sunday. So we're keeping the applications open all this upcoming week. So we really encourage you to tell your friends and your school communities and post about this. I'll be sharing some more social media posts that you can put out. Would love at the end, you can tweet us. We just started a Twitter. We need followers, we need friends, but please help spread the word, especially in underserved communities or groups. We want to make sure, again, this is accessible and that we are building an inclusive future quantum workforce. So please make sure you're sharing this with your friends and colleagues as well. And without further ado, I'm going to turn it over to Fran and Amir, who will get us started on what actually is quantum computing.
Awesome. Thanks for going through all those logistics, Kira. And I will share my screen. Let's present. All right. Can you see everything?
Yes.
Yes? Okay, cool. So as Kira mentioned, now we're going to have a little bit of fun and sort of go through quantum computing at a very high level, sort of just to give you a taste of the types of things we're going to be learning about and working towards in this course. But before we go into that, Amir and I thought it would be fun to give you a sense of what our quantum journeys looked like. So I will pass it to Amir to talk about his quantum journey.
Hi, everyone. Again, I'm Amir. I'm very excited to be teaching this course alongside with Fran. So I'm going to start with like my life journey. I was born in Tehran in Iran, and then I moved to California where I finished my high school, and then I moved to Boston for, well, actually technically Cambridge for undergrad, and then I stuck around for my PhD. So I first came across quantum computing my freshman year through my advisor, Seth Floyd, actually, who's one of the founders of the field. And I became very interested in the fact that we could again take the weirdness of quantum mechanics, like the fact that it's unintuitive, and put it to use to do things that we normally can't do. So I started getting into quantum computing. I began research in the quantum photonics lab under Dirk England my freshman year at MIT, working on photonic quantum computation. And somewhere along the line in my undergrad journey, I started teaching an intro to quantum computing course at MIT. And that's actually where I met Fran, your other instructor. She was my first student and who came along board with the class in the future years and drastically improved it. And then the other part of my journey is, again, I wanted to do quantum computing since undergrad, and I stayed at MIT for grad school to continue working on quantum computing. I switched lab to Will Oliver's Engineering Quantum Systems lab, where we focus on superconducting qubits as a medium for experimental quantum computing. And we'll talk about superconducting qubits more as we go along the course, but it's the same technology that big companies like IBM and Google are using. And somewhere along the line, I worked on a project, which we're going to actually hear briefly about, where we studied the effects of ionizing radiation on our quantum bit quality. That was with a postdoc, Antti, and again, with your other instructor, Fran. And that work recently got published. And nowadays, I'm working on simulating physics and many body systems using quantum chips consisting of 9 and 16 qubits that's a figure that, and the chips that we use, the quantum chips that we actually use, is a figure that you see on the bottom right of your page. And with that, I want to pass it along to Fran for her intro.
All right. Thanks, Amir. So I guess now I'll briefly run through my quantum journey. So when I first got to MIT, I hadn't done much in the realm of physics beyond just taking the standard high school physics, classical mechanics courses. That being said, my junior year in high school, I had the neat opportunity to visit CERN, where I got to learn about the Large Hadron Collider and was kind of exposed to the notions of quantum mechanics and high energy particle physics, but didn't really know what was going on. And when I went to MIT, I thought I was for sure going to do just electrical engineering or computer science. Now that all changed for me when at MIT I took my two sort of required physics classes, classical mechanics and electromagnetism. And I had a really great professor, Christoph Paus, who actually was a CERN researcher himself. And he somehow found a way to sort of integrate all of these really wacky ideas from quantum mechanics into our standard classical mechanics physics courses. When he was explaining potential energy diagrams, he would talk about things like quantum tunneling. And that really blew my mind and made me interested in physics. And so I ended up picking a double major. That being said, my first 2 years at MIT, I did quite a bit of research, but primarily in EECS labs. So my freshman year, I was working in CSAIL at the NET MIT group on localization detectors that could see through walls using Wi-Fi. I then did a summer internship at the NASA Jet Propulsion Lab, where I did ground communications research for the Deep Space Network. And then finally, I joined the camera culture group of the MIT Media Lab, where I was working on LiDAR and improving the performance of machine learning. And while those were all really cool and fun, there was something sort of in the back of my mind that always said that I wanted to do something more on the lines of physics and fundamental physics. And additionally, as Amir sort of mentioned in his journey, my freshman year, I had the opportunity and privilege to take Amir's first pass at the Intro to Quantum Computing winter term course. And that was the first time I really got exposed to quantum computing in depth. And I thought it was super cool. And my favorite part of it, I think, was that it brought together all of these interests: electrical engineering, computer science, and physics. And I knew that I wanted to try doing research in the domain of quantum computing. And Amir actually recommended that I join the engineering quantum systems group, which he too would also join at some point. And this was under the supervision of Professor William Oliver. During my 2 years in the group, I got to work on a ton of really, really cool projects. I started off working on quantum state tomography, which allows us to figure out how, what the quality of the states are that we're actually building inside of our quantum computer, given that when we perform measurement, we can only see classical bit states. This was with a postdoc Martin and a graduate student Tim. This project actually ended up being applicable to a waveguide quantum electrodynamic project. I know that's a lot of complicated terms, but it was a really fun project I was working on with a grad student named Barath. On there, I was kind of just working on improving runtimes of our processing code so that we could process billions of data points that were necessary to come to conclusions. And then finally, I joined the QubitxQubit project with Antti and Amir. There, I was mostly building machine learning and data analysis tools. So I guess a common thread through all of my projects in this group was that even though it was a quantum computing group, I was mostly doing a lot of EECS work, programming, and analysis. So even for those of you who might be coming in with less physics background, there's still a lot of cool work that can be done from more of an electrical engineering or computer science side, kind of going back to what Abe said earlier. During my time in the group, I also had the chance to do 2 summer internships, one at Rigetti Computing and one at Microsoft Researcher under the supervision of Dr. Marcus Da Silva, working on some really cool quantum machine learning for quantum computing, as well as statistical machine learning for quantum error analysis. And this was through these experiences, I kind of realized that I was very interested in exploring further the intersection of machine learning and quantum computing, which is actually what I will be pursuing at Berkeley later on under the supervision of Professors Umesh Vazirani and Michael Jordan. And note that indeed one of my supervisors has the same name as a very famous basketball player, but I don't know how good he is at basketball. And I guess for right now, I'm here at the University of Oxford doing a master's in statistical science, trying to learn a bit more theory since I come from applied background, but want to do more theory work in the future. And alongside of my work here at Oxford, I get the pleasure of teaching all of you through this course that I'm really excited about. So with that, Amir and I actually wanted to show you a video that was made about a project that we worked on together, the QubitxQubit project that we both referenced. And I think it'll be fun because it kind of goes through quantum computing at a very high level and will also allow you guys to see what a superconducting quantum computing lab looks like from behind the scenes. So for those of you who are more experimentally oriented, this is kind of a taste of what you would see in the lab setting. And Kira, let me know if the audio doesn't work for some reason. Hi, my name is Francisca Vasconcelos, and I'm a senior undergrad researcher working at the Engineering Quantum Systems group at MIT. This group is a lab within the MIT Research Laboratory for Electronics that focuses its research specifically on quantum computers. The difference between a quantum computer and, say, a computer that one of us uses is computing power and speed. There are certain types of algorithms which would take thousands of years to run on even the world's fastest supercomputer. However, there are also quantum versions of those algorithms that can be run on a quantum computer in solely a matter of minutes. At the moment, the group works a lot with 5-qubit samples. You can think about a 5-qubit sample as a single puzzle piece within a much larger 10,000-piece puzzle. Computers require millions of transistors in order to be useful, and we aim to eventually build a quantum computer with hundreds of thousands, if not millions of qubits, so as to perform even more powerful computations. A big challenge that quantum computers currently face is noise, and that's what a lot of the group's research currently focuses on. One of the current objectives of the lab is to reduce the amount of noise associated with each of these samples. This is so that when we put them together, we can have a working quantum computer. One of the hypotheses that we're trying to figure out is whether background radiation contributes to noise within our samples. So, how we're going to test this hypothesis is by first putting one of our samples in this special dilution refrigerator. This refrigerator cools down the inside temperature to close to absolute zero. We need to do this in order for the 5-qubit sample to operate. We are going to run 2 experiments simultaneously. The first is a control experiment in which we leave the fridge uncovered and exposed to all the background radiation. Every 10 minutes, we swap to our second experiment by lifting a shield of lead bricks to surround our fridge, reducing the radiation it sees by a factor of 10. We continuously swap between these 2 experiments every 10 minutes, lifting the shield up and down around our fridge. By measuring certain properties of our qubits, we can see if the qubit performance is hurt by the radiation. Through repeated measurement and statistical analysis, we hope to see that the lifetime of the qubits is reduced when the shield is down and they're exposed to radiation.
So with this data, right now what we see is that for our long-living qubits, the mean of the distributions actually do start moving apart from one another. So when the lead shield is down, we see a lower lifetime mean than when the lead shield's up. Also, we see that the distributions start to move apart from one another. Granted that we need more data at this point, but based on the measurements on the 5 qubits that we're making simultaneously, we anticipate that with better qubits and more data, we will see that canceling of background radiation will lead to an increase in the lifetime of the qubits. So, in looking at the data from our experiments, there seems to be less noise in the qubit samples when we use lead bricks to protect them from radiation. This means that future full-scale quantum computers may require some sort of radiation protection.
At the end of the day, with our research, we are trying to bring full-scale quantum computers a little closer to reality. All right, so I hope you guys all enjoyed that video. If you're interested in learning more about the project, we actually did finish it and publish it, as opposed to kind of what Amir was referencing, that we need more data. So if you are interested in learning more, we're happy to share this video or the paper, or potentially give like a separate talk about it. But with that being said, I will pass it to Amir to begin describing what quantum computing is.
Okay, thanks again, Fran. So let's start by talking about what does quantum actually mean. So we heard the term quantum all around. It's something that I feel like usually gets misused even in some contexts. But so we're going to break it down to two parts. The first part is quantum mechanics, which describes how objects behave at small scale. So you can think about it again as like the behavior of atoms or things that are counterintuitive with the world that we see around us, which we refer to sometimes as a classical world. Again, these counterintuitive effects at times seem incompatible with the things that we see in our day-to-day life, but we'll see actually how they end up relating to one another. And on the other hand, we have quantum computing, which uses quantum phenomenon, again, phenomenon that are common in quantum mechanics, to perform computation. And again, the whole point of quantum computing is that we take the counterintuitiveness, the weirdness of quantum mechanics to somehow boost our computers. And we will see how that leads to us being able to solve certain computational problems that normal computers cannot. So again, to reiterate, quantum computing is an application of quantum mechanics. Now, there's quantum computing, there is quantum communication, there is quantum key distribution, for example, and all those are applications of quantum mechanics. So why go quantum? Well, the main reason is because some problems that we are facing today are just too hard for classical computers to solve. So let me give you two examples. The first example is chemistry simulations. When you think about it, at the molecular level, all chemical reactions, all phenomena is governed by quantum mechanics rather than, again, the classical mechanics that we're used to in our day-to-day lives. And it turns out that our classical computers are really, really bad at simulating or replicating these processes. We'll discuss why in further lectures, but just keep that in mind. So that's why one of the first applications of a quantum computer would be to perform chemistry simulations. Now, why do we care about chemistry simulations as a civilization? Well, when it comes to generating a vaccine or coming up with new medicine and treatments, something that we need to study in depth before actually producing, again, this vaccine or this medicine is how do the molecules of this vaccine or, again, medicine react with whatever we're trying to fix. So our classical computers, again, are really bad at making those simulations. Which leads to us having to go through a lot of trial and error in lab to come up with something that's effective. Now, if we have a quantum computer, we could, again, understand these processes better, engineer more effective and less costly treatments, and then proceed that way. And again, the benefits of that are twofold. The first one is that we're going to have more effective medicine, and the second part is that the cost and the time to actually produce new medicine or vaccines is going to be much shorter. And another application is for factoring. Now, you might ask, what is the significance of factoring? And it turns out that most of our classical encryption today that we're commonly using is based on the fact that factoring large numbers is actually a very difficult task for classical computers. Whereas with the quantum computers, it has been shown, and again, we're going to talk about this later in the course, that you can take a very large number and factor to its 2 prime factors. Now, here's a caveat for classical computing, at least. So over the past quarter century, we've gotten accustomed to our computational power growing exponentially. And this growth is governed by something called the Moore's law, which again states that computational power gets doubled every month. But again, every 18 months. But as we're progressing, as we're making these transistors smaller, which again leads to us being able to fit more transistors or computational elements on a single chip, which leads to increasing power, we start hitting a wall where quantum mechanical effects come into play and actually disturb our classical computing. So again, if you look at the chart that we have, the plot that we have here, the transistor, the solid state transistor was roughly invented in the early 50s. And ever since, we've seen, again, a doubling and exponential growth in our computation power. But over the past decade almost, this progress has slowed down, which makes us begin to wonder how much longer can we actually sustain the growth and how do we address the problems that are still unsolvable? Because we can't just make larger, more powerful classical computers. So with that, we're going to make the claim that since we're approaching the end of Moore's law, we need to look at other technologies, and quantum seems to be a great candidate. So let's talk about a qubit of quantum history, and there's pun intended there. So the concept of quantum computing was introduced by the physicist Richard Feynman in 1981, where he proposed a framework for simulating the evolution of quantum systems with some other quantum systems, or with some other quantum system, i.e. a quantum computer. And this was a cool niche idea for physicists. They toyed around with it a little bit, but the field didn't get as much momentum until 1994, which is when Peter Shor showed that quantum computers can factorize large integers efficiently. And again, this has a lot of security implications, and we're going to talk about this a little bit further. But this theory was basically what kickstarted the field almost, in the sense that people started paying a lot of attention to what are the capabilities of quantum computers and what does it take to actually build one. Now, in 1998, we got the first demonstration of a quantum algorithm. I mean, the quantum algorithm wasn't anything too fancy. It only involved 2 quantum bits, but still, we managed to show as a field that it is possible to control these quantum systems. And then fast forward all the way to 2012, there were demonstrations of quantum processors with 3 qubits, and some error detection and some more complex algorithms were implemented using this. Now in 2017, IBM provided access to their 5-qubit quantum chips through the cloud, which basically now meant that you or anyone around the world could go make an account and actually play with a quantum computer without having to go in the lab like Fran and I do on a daily basis. And then, well, this is not finally, but the most recent milestone was in 2019 when there was a quantum supremacy quantum supremacy demonstration where we were able to show that quantum computers are able to do a task that no classical computer, including supercomputers, can replicate or can do better within a reasonable amount of time. So I think for the task that it took a quantum computer roughly 100 to 200 seconds, it was shown that it would take a supercomputer about 10,000 years to replicate the same task. Now, there are many technologies out there to be used as a quantum hardware platform. So again, we talked about the normal transistor, how in the 50s was when we finally converged on solid state transistors, which is more or less a technology that's in use today. But the jury still seems to be out on what is the best qubit technology, or you can think of it as the best quantum transistor in some sense. So we have a few different technologies here on this slide. I'm not going to go into detail because we would require some physics, but as of today, it seems like superconducting qubits and trapped ions could be a candidate for realizing a universal quantum computer with error correction, like a perfect universal quantum computer. And superconducting qubits is actually the technology that IBM, Google, and most leaders in industry are using today. And finally, just to give you guys some point of comparison. So I want to compare an early classical computer to a current, which is early stage quantum computer. So the figure that you see on your left is ENIAC, which is the first electronic digital computer. Was demonstrated in 1946. It was the size of a room, and it had less power than the smartwatch I'm wearing right now. Now, in comparison, there's a 54-qubit superconducting quantum computer that was used for the quantum supremacy demonstration. And already at this early stage, this quantum computer is able to outperform all the classical computers in the world at some task. And there's only room for growth from here. Now, there's a very vibrant community and landscape today. So in 2019, rather, there are companies that are focused on quantum applications. Some companies are focused on quantum hardware and anywhere in between. And what I'd like to compare this figure that we have on this paper, on this slide to, is back when I started my undergrad, I think there were maybe a handful of companies max working on quantum computing. There was IBM, Rigetti was just starting, there was D-Wave, and a lot of these players were not in the field. And over the span of the past, I would say 5 to 6 years, we've seen a large growth in the quantum computing landscape, and we only anticipate it to get larger in the future. And finally, quantum computing can be applied to many different areas. So we briefly talked about chemistry and medicine, but it could also be applied to machine learning, agriculture, finance, biology, cryptography also we briefly mentioned, and of course fundamental physics, which is what it was initially proposed for. And again, there are so many more applications that we can't even think of right now. And again, to make that point, if we put ourselves in the shoes of a classical computer scientist in 50s and 60s, no one could have thought that computers will be used for everything in our daily lives, anywhere from communication, like rapid communication with our family members, through texting or the internet, or really TikTok or any of the application revolution. So there is still so much that we don't know. And lucky for you guys, you will probably be the people who make the first quantum applications.
All right, I will pick it up from here. Thanks for that, Amir. So Amir did a really good job of sort of motivating why we want to build quantum computers and going through all of their different applications. I want to use the last part of this lecture to explain or start trying to explain what a quantum computer and what these qubits actually are. And of course, just another reminder, this will be a very high level, somewhat abstract introduction to a lot of topics we'll be seeing later in the course. So if you don't understand something, don't feel bad about it. We will be going through all of these concepts in a lot more depth later on. Also, don't feel the need to take notes. We won't be quizzing you or anything on any of this. This is just for you guys to start to get a sense of what you will be learning about. So I want to start off by talking about the field of quantum computing as a whole. And as has already been mentioned a few times throughout this presentation by Abe and myself, quantum computing is an extremely interdisciplinary field. Actually, building quantum computers lies at the intersection of math, electrical engineering, physics, computer science, mechanical engineering as well. And then, of course, there's applications to a huge number of fields, as Amir began to indicate. So we now want to ask, what actually is a quantum computer? And it turns out this isn't a very easy thing to define at a high level to someone coming in with potentially minimal background. So I decided to throw in Amir's carefully crafted cocktail party definition, which he has refined over the years to tell random strangers he meets on the street when they ask what he does research on. So in Amir's words, in quantum computing, we use the weirdness of quantum mechanics to solve problems that normal computers cannot. And I think this is a really great definition, and over the next few slides, we'll be diving into exactly what we mean by weirdness. But before we do that, I know you guys have heard the term qubit mentioned a lot, so I want to just take a few minutes to go through and really try and explain and start to give you an intuition for what the difference is between a qubit and a bit. So let's just start off with a bit, which is the basic unit of information processing in classical computing. As Amir mentioned earlier in the talk, the fundamental hardware in a computer chip is a transistor, which you can think of as just an electrical switch, and it either allows electricity to pass through or not, and it can take a state of 0 or 1, on or off. So you can think of this like a light switch, essentially. Now, in a quantum computer, we have what's called a quantum bit, which is abbreviated as a qubit. And in these qubits, it's similar to a bit in the sense that it is a two-level system, meaning similarly it has an on-off state, 0 or 1. However, different from a standard classical bit, it isn't confined to just take the state 0, 1. It can actually be a combination of 0 and 1 simultaneously. And in the next few slides, we'll dive a little further into what that means. But for now, if you're picturing a bit like a switch, you can picture a qubit more like a dial, where you can rotate this dial to sort of move between the states 0 and 1 and create what we call a superposition between them. So now the basis of quantum computing, as we've mentioned many times, is quantum mechanics. And it turns out that there's three sort of really wacky but core ideas in quantum mechanics that give us the weirdness or power that we utilize in quantum computing. And these three properties are superposition, entanglement, and quantum interference. And we'll be going through each of these properties really quickly right now, but again, we'll explore them further throughout the course. So let's start off with the superposition. This is a really fun idea, but somewhat hard to wrap your idea around, so I'll try to explain it in a couple different ways. Essentially, what a superposition says is that a quantum system can exist in two states as one. This goes back to that notion we were talking about of a dial, where you're saying our qubit isn't constrained to just being 0 or 1, but can actually be 0 and 1 at the same time. Now you might wonder, what does it mean to be both 0 and 1? Well, it turns out that a qubit, when it's in a superposition, it is both 0 and 1 at the same time, but then when we as humans observe it or perform a measurement, this qubit collapses to be either 0 or 1. It collapses to the classical bit states. And this is a really, really weird property of quantum mechanics, right? It means that by us observing a quantum state, we actually change the property of the quantum system. We collapse the state. And this has all sorts of interesting ramifications, and there are whole fields of philosophy just dedicated to grappling with this notion. There are also some theoretical physicists who still are fundamentally opposed to this idea and working on alternative theories. So it's a pretty interesting notion. And I guess for those of you who are interested in popular science, one example of this that you might have heard of is the classical thought experiment called Schrodinger's cat. And in this thought experiment, essentially, I'll go through it really quick. You have a cat that's inside a cardboard box, and inside that cardboard box, there's also a little vat of poison. And above that poison is an apparatus that has a radioactive isotope in it. And that radioactive isotope has a certain probability of decaying within the next hour. We'll say for now that it has a 50% chance of decaying and 50% chance of not decaying. And if the radioactive isotope decays within the hour, the hammer will come down, hit the vat of poison, and kill the cat. If there's no decay, the hammer will stay upright and the cat will live. I know it's a bit grim, but this is a historical anecdote, so we'll roll with it. And so essentially what happens in this thought experiment is we say, okay, let's close the box, leave it out for an hour, and then come back and try and figure out what happened to the cat. So within the hour, we know, right, that the radioactive isotope could have either decayed or not, but we're not sure what happened since we can't yet open the box. This means that there's a 50% chance that the cat is still alive and a 50% chance that the cat is dead. And thus the cat is in a superposition of being both dead and alive. However, as soon as we open the box, sort of analogous to a quantum measurement, we can determine whether the cat is alive or dead. And once we do so, we know for certain the cat is alive or dead. So there's a 100% chance that the cat is alive or a 100% chance that the cat is dead. And so that is Schrodinger's cat, and that's meant to illustrate the idea of superposition. There's sort of a modern meme that is inspired by Schrodinger's cat, which I really enjoy, called Schrodinger's phone. And essentially, this corresponds to the case when you have your cell phone, you drop it, and you're really anxious as to whether or not you crack the screen. So while the phone is lying face down, you aren't sure. There's a 50% chance or less or more that it cracked and 50% chance it didn't. And you don't know for sure until you pick it up and actually look at the screen, in which case you know it's cracked or not. All right, so that was superposition, and now let's move on to entanglement, which is another really wacky idea. And I want to kind of give some historical context, which I think is kind of fun. So many of you probably know the scientist Albert Einstein for his work on relativity and his famous equation E=mc². However, Einstein didn't actually receive his Nobel Prize for his work on relativity. He in fact received it for his work on the photoelectric effect, which we will be learning about later in this class, which was one of the fundamental experiments in pioneering the field of quantum mechanics. And that being said, although Albert Einstein created the field or started a lot of the research in quantum mechanics, he was very opposed to some of the ideas that fell out of it, specifically this idea of entanglement. And he was so concerned and he didn't like it so much that he called it spooky action at a distance. Now let's dive in and see what entanglement actually means. So entanglement is the idea that if you have an entangled pair of particles or more, one of the states of one of the qubits or quantum particles cannot be described without the state of the other. So, and this holds over distances. So one example that I really like to use to explain this concept was told to me by an older student at MIT who did research at Caltech. And this was how he described it. Imagine we have two boxes and we have a pair of gloves, one that's left-handed and one that's right-handed. We randomly put the left-handed and right-handed glove in each of the two boxes and we shuffle them around so that we don't know which box contains the left-handed glove and which contains the right-handed glove. Now, I take one of the boxes and you take the other box and we walk all the way to opposite ends of the galaxy. Now, if I open my box and, for example, see that I have a left-handed glove, you instantaneously know that you have a right-handed glove. And this is a really strange phenomenon because even though we're at opposite ends of the galaxy, this information transfer is actually instantaneous. And part of the reason why Einstein didn't like the idea was that it actually seems to contradict some notions of relativity, including the notion that information can't travel faster than the speed of light. So that's entanglement in a nutshell. And with that, we'll move to our final wacky aspect of quantum mechanics, which is interference. And the high level idea here is that quantum objects, although we often think of them as particles, they also can interact like waves. And this is the notion of wave-particle duality. And in the course, we'll be learning about the double slit experiment, which is one of the experiments that led to this idea. And so essentially what this means is that the probability amplitudes of particles and quantum states can constructively and destructively interfere to create peaks and crests that we call quantum interference. And this is actually super important in creating quantum algorithms that can do things which classical algorithms cannot. Again, I'm not going to go into a lot of detail here, but that's quantum interference at a high level. And so now that we've sort of been introduced to these three weird aspects of quantum mechanics, I just wanted to conclude with a final statement, which is that these three weird quantum properties enable the design of quantum algorithms, which can compute in ways that classical computers cannot, making quantum computers more powerful for solving certain types of problems than classical computers. And I want to emphasize that. So I think there's a general misconception that quantum computers will essentially just take what classical computers do and do it faster, but that's not really the case. The cool thing about quantum computing is that it's a whole sort of new way of thinking and designing algorithms, making use of these properties that qubits have, which normal bits don't have, to gain what we call a quantum advantage. And then I just wanted to conclude sort of by talking a bit about the future of quantum computing. Earlier in the talk, Amir mentioned Moore's law, which told us that classical computers would improve exponentially in the years to come. In recent years, we've seen quantum computers have actually also undergone a similar exponential increase in improvement, whether that be in terms of computing power, number of qubits, and other metrics. And so there are a few famous folks in the field who have created their laws saying that they believe that this exponential improvement will continue in the years to come. Of course, we don't have that many data points to really work off of, so no one knows for certain if that will be the case, although of course we would love it to be. But that being said, that's really exciting for all of you getting into the field because you can help make that exponential growth a reality. And to sort of conclude with our future of quantum computing, I wanted to pull up roadmaps from two of the industry giants, IBM and Google AI Quantum, who have very recently actually released these roadmaps for their plans to building larger quantum computers. And so essentially what you see is, as of right now, the largest quantum devices available are on the order of 60-ish qubits. But both of these companies have plans to reach over 1,000 computers by 2023. So within the next few years, and probably by the time that many of you are graduating from college, you will be able to run algorithms on quantum devices that have over 1,000 qubits, which is really exciting because then you'll really start to be able to get in the realm of significantly outperforming classical computers. So I think it's a really exciting time to be getting into the field, and there's a lot of interesting work to be done in the years to come. And with that, let me just check the time. Oh, we do have time. Awesome. So I wanted to end the talk essentially by showing you all the video that I actually stumbled upon when I was in high school, which was the first time I ever heard about quantum computing. It's a video by a YouTube channel called Kyrgyzat, and I think it does a really, really good job of explaining quantum computing and has really nice visuals. So I'll play it for you all now.
For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 40 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those. It can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double-check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email, and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. but a quantum computer with exponential speedup could do it in a breeze. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures, such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. This video is supported by the Australian Academy of Science, which promotes...
All right, I hope you guys all enjoyed that video. I've watched it several times, probably more than 10 times over the past few years, and I feel like every time I watch it, I enjoy it even more. Again, if not everything made sense to you today, that's totally okay. When I was in high school, most of this video didn't make sense to me, but you guys are all super lucky that you get to take a class where you'll actually get to go through and learn a lot of these concepts. I really wish I had a class like this when I was in high school. So with that, I think I will pass it back to Kira to go through some announcements.
Awesome. So just a few more minutes, everyone. So just hang tight. Again, would like to thank everyone that has joined the call today and participated, as well as Fran, Amir, and Abe for, bestowing your wisdom in quantum and showing us so many awesome things that we have ahead of us. This is just the beginning. I want to go through just a few very practical things. So in terms of the Discord, again, if you don't have your ID yet, please email us. Again, we'll be working through that as soon as possible. If you, we're going to change actually the Discord protocol right now, where you will submit to us a channel that you want and we will create it, or we will delete it based on the owner and the kind of the owner's decision. So we'll be sending some information around like that. We want to start highlighting some of you and why you are in this course. So we'll also send out more information about, what we're looking for, a photo and some basic information, but we do want to include all of that. And then, as I had mentioned, applications are still open. This course is open to anyone who has basic trigonometry. We are going to try to have a trigonometry review session for anyone who feels like they're rusty, or, it's been a while, or they're not exactly sure what knowledge they need to be aware of. I'm going to be taking this course as well with all of you, so I'm definitely going to be attending that session. We'll provide more information about that. We're assuming likely it will be on Saturday after our panel discussion. But yes, applications are still open. Definitely, would love to get more high school and university students, particularly those from, underrepresented, underserved backgrounds, but everyone is encouraged to apply. Please make sure that, you're sending this information out to your schools and to your friends and over social media. We'll share some things that you can share on social media as well. So you can really help us spread the word and make this the best program possible. So homework for this week, really not a lot of homework. Sorry, it says familiarize yourself with Piazza and Discord, just Discord this week. We'll be waiting to get everyone on Piazza next week, and we'll talk about that more in detail. So please read through the student handbook and go through Discord. We'll be sending out information about the labs later this week. So when we send that out, please fill that out. And then we'll also send over some optional fun readings that all of you can do. Next Saturday, because we do not have a lab this week, we will be having a panel discussion with some of our Qubit by Qubit academic staff. Many of them are our teaching assistants who have a ton of experience in quantum computing and have a lot to talk about in terms of why they got into quantum. We will be taking questions from all of you that you'll get to ask. So we'll also send over the protocol for how you can ask a question to our amazing panelists. And then last but not least, Frank, can you go to the next slide? Please follow us. Again, we're really trying to boost our social media following. The QXQ, actually don't use that because there's already people using that apparently. Just use the hashtag QubitxQubit. Everything has been sent to you. Gabby has sent it out where you can follow us. Please follow, please retweet, please, share stories. Again, get people interested in this course and in quantum computing. It's such a new field. And there's definitely, we can reach a lot more people with all of your help since you all are from around the world and have a lot more reach than we can by ourselves. So again, we just want to thank you so much. We are here for you. We are excited to be on this journey with all of you. This is going to be incredible, and we can't wait to see what you all do. So please, again, be patient this week as we sort through all of the logistics, but we promise we'll get to everything that we need to get to. And yeah, I'll stick around for a few minutes to answer some questions, logistical questions that people have, and then we'll cut it off at 1. But you're welcome to go at this point. So thanks everyone again. I will open up the chat. Okay, awesome. So registration is likely going to close on Thursday. We may keep registration open beyond that. We're not sure, but please we want to get in all the applications by Thursday. Thanks everyone for being so excited about this. The lab exercises will be different from what you do in lab will be different from the homework. The problems for part of the lab will be similar, but that's mostly just to help you so you can know how to do the homework. Let's see. Okay, there's a lot of questions. Can some videos be shared for how to use Discord and the other platforms? That's an awesome idea. Rachel, can you please make sure that's noted down? Yes, we will try to do that. We might even have some office hours so we can go through tutorials and troubleshoot. Again, it's hard to do things one-on-one, but we can possibly get students up like this. If we're taking this course for a grade through our school, will we still be able to resubmit assignments that we're not satisfied with before the due date? Yes, you can submit as many times as you want. The way it will work is you'll submit an assignment and it will tell you right away, oh, these 5 questions are wrong. And then you can go back and work through them again up until the submission time. Again, if we're finding out that the homework problems are too hard and people are really struggling, we'll lower the grade requirement and what the threshold is. We're not, again, trying to be here to make this a difficult course. We want this to be fun and energize you for the future. Yes, if you can't make the panel next weekend, there will be a recording available, no problem. You do not need to buy anything for this course. You do not need to pay for anything. Again, if you have previously paid anything, you will be refunded. But in terms of books, you don't need to buy anything. We put some optional book recommendations on there. Those are only if you want to read those and go further. If you are interested in having your school partner with us and you are a teacher or you are a student who wants your school to partner and offer this for credit or offer as an after school class, we would love that. Please email Kylie@thecs.org. Gabby, if you can post that to everyone, that would be amazing. Is the homework lab paper-based? No. We are in the 21st century. You will do everything online and submit, and it will be electronic and easy and automatic, and hopefully it'll make it super simple for both us and you. So you don't need to have a scanner or anything like that. Again, you do not need to buy any books, please. No, you don't need to buy anything.
I just want to add to that we are developing a textbook specifically for this course. So any content that we cover in lecture will also be covered in that textbook. We'll also be sending you guys optional readings. If there are like open source PDFs, we will make sure to link to them. For some of the optional readings, of course, they are books. And while you might be able to find free versions online, in order to protect the authors, and because we shouldn't be doing that, we're not going to be sharing PDFs for those resources. But if you dig around, you might be able to find free PDFs to those as well.
And oh, I love this question. If my dad asked to attend alongside me, am I allowed to? Yes, we would love that. That would be amazing. Very, very happy for family members to sit in. The thing that's really not okay or acceptable is you sharing the link or you sharing all the recordings and homeworks and you know, readings that we send out. Those are only for personal use. Like if you are sharing those in a larger community, that is where problems arise. What section of this course would you say is your favorite section? Amir and Fran, do you each want to just mention for a hot second what like what you love most about quantum computing or what you're most excited to teach?
So I guess I will be teaching actually a large part of the content this semester. And while I know for many of you it'll be a review, this actually goes back to my anecdote at the beginning of why I found quantum mechanics very hard when I started off. I hadn't taken, or I guess I didn't have, I think, the mathematical maturity I needed when I stepped into quantum mechanics. So I'm really gonna put a lot of emphasis on making sure we teach you guys all the math you need in order to succeed in the second semester. And that's gonna involve some linear algebra, some probability, complex numbers, and it'll be a lot of fun. That being said, on the quantum side, I think I'm very interested in information processing, and a lot of the algorithms and protocols we'll get to explore. Amir?
Yeah, I think for me, it's probably mostly quantum circuits and their applications. And again, how you can do things with even limited resources that we have available today. Like let's say on an IBM, on a 5-qubit IBM device that you can't do with a normal computer. Like for example, how can you create, this entanglement, which Fran was talking about earlier? Or quantum teleportation. I know that makes Kira happy.
I love teleportation. I'm so excited for all of you. Lectures will all be, at least for now, until Canvas is up and running, we will add them to the Discord channel. So you will have access to them again once this finishes. Will you have to Fran?
There was one project that I saw that I don't think we actually mentioned during the lecture, but we are planning to have a final project component in second semester, which will be a lot of fun, where you guys get to take all of the things that we learned about in class and apply it to some application of interest. So for those of you asking about projects, there will be a project component in the second semester of the course.
So in terms of you being able to view your grades or how you're doing, we're still sorting out the logistics of how that would be able to work. So at this point, unless you're actually taking this, we will notify you if you are in danger of not passing the class. Definitely you will hear from us, but and we'll work with you to, make sure you do. But in terms of actually being able to see your percentage grades, unless you are through one of our partner schools or receiving it for a grade for course credit, at this point, we won't be able to, whenever you're interested, check in and see your grades. Again, there may be options as we get Canvas downloaded and ready to go that you could be working on that. Is this course considered a career technical education course? I'm not sure what the exact terminology would be. Again, there's so different schools use so much different terminology, but definitely we'll send out the information later this week and you can present it to your school and see if they'll be able to give it for credit. In terms of when the recordings will be available, we'll try to get them out as soon as possible. It takes a while for them to download and get ready. So that's basically the only thing that we have to wait for. And yes. Okay. So it is 1:01, well, 4 p.m. Eastern Standard Time. Thank you all so much for attending. We're so excited again to kick this off with all of you, and we will see you on Saturday for the panel discussion. Thanks again, guys.